Hello, guys. We are moving on to our next lesson, which is all about exponential growth and decay. So, when you hear that, when they're talking about real life statistics and saying that, the flu, the number of people with the flu is rising exponentially, or um, the value of your car is decreasing exponentially, stuff like that, that's what we're going to be looking at today. We are going to be making a foldable. It's this one that says exponential growth and exponential decay on it. So you're going to want to tear this guy out. And it should have a backside like so. Okay. And then you're not going to fold it quite in half, and you don't have to cut around the outside or anything. You can just leave it as it is, as the full sheet. And you're not going to quite fold it in half. So notice here how I folded it over so that exponential function word problems is still showing. But then also exponential growth and decay are showing as well. So just want to make sure that you guys see how that's made. And then we cut along that dashed line to make the two little flaps. And then I glued it into my notebook. If you have not made this yet, go ahead and pause the video and make it. This is what it's looking like. If you have made it, we're going to go ahead and switch over, and we are going to fill out this foldable, and we're going to start with just looking at exponential growth right here. Okay, so let me go down a little bit more. There we go. So in exponential growth, the A, here's the general equation that you'll see it in, or you'll be writing an equation that looks like this, okay? A is always your initial amount, meaning how much money did you start with, or how many people were there at the beginning, or things like that. Okay. R is always your growth rate. So how much is it growing by? Typically, you will get your growth rate as a percent, so you would have to convert it to a decimal. Okay, the growth rate in this equation has to be in decimal form. And we'll look at how do I convert from a percent to a decimal. And then T is time. And time depends on the problem, right? Could be asking you, maybe it's growing a certain amount every day, so then time would be in days. Or maybe it's growing a certain amount every year, so then time would be in years, right? So let's look at an example here. Example number 1. It says the exponential function below models the amount of money in Jose's savings account, where X represents the number of years since he invested the money. Okay, so X is in years, so time is years. It says, what does the 3,000 represent? Well, if we look at our equation up top, okay, this is in front, so this is my A. This is my initial amount. So this is how much Jose invested in his savings account. His savings account. All right. Then part B says, what is the growth rate? Well, if we look at the equation, the thing that has the exponent of x is 1.06, right? And that equals 1 plus r, because that's what's in the equation. So I'm going to scroll up, but all this stuff is going to stay the same. So right here, 1 plus r is what is being raised, or is the base of my exponent. So here, 1.06 is the base of my exponent. So if I minus 1, right, I get r is equal to 0.06. Now, the growth rate is always when it's in the equation, it's in decimal form. But when I just want to know what is the growth rate, it needs to be in a percent. So I need to change this to a percent, right? And the way that you do that is you take your 0.06 and you always move it 2 decimal places to the right. 1, 2. So this equals 6%. Okay, so the growth rate of this bank account is 6%. Okay. And then if you were going the opposite way, right? If you had percent, here's the decimal place, you move it to the left 2, and you get 0.06. So that's kind of how you go back and forth. You always move it 2 decimal places. Okay, let's look at another one. Example 2 here says the cost of tuition at a state college is $8,500 and is increasing by 3% a year. What is the cost of tuition after 6 years? Okay, so because it's increasing 3% a year, T has to be in years, and here it's years, so we're good. So we're going to write the equation. F of x equals my initial amount, which is 8,500, times 1 plus my growth rate. Well, my growth rate has to be in decimal, right? So if I take 3%, here's my decimal place. If I move it to the left 2, I get 0.03. So this is 1 plus 0.03, and then to the 6th, because that's how many years. Okay, so I'm going to have 8,500 times 1.03, right? 1 plus 0.03 is 1.03 to the 6th. When I enter this into my calculator, I am very, very careful about parentheses. I do 1.03 to the 6th, and then I multiply by 8,500, and we should get about $10,149.44. Okay, but because this is a word problem, we have to answer it in a sentence. So I can say tuition will be about, because it's not exact, and then I can say $10,149.44. And there's my answer. Okay. Last problem here is example 3. Sally deposits $10,000 into a bank account that earns 4.7% interest compounded yearly. What is the balance after 5 years? So again, let's write the equation. Since the interest is compounded yearly and I want my answer in years, I don't have to change anything, so that's good. So here I have 10,000 is my initial amount, and then 1 plus, now 4.7%. I have to move that decimal place over twice, fill in any zeros. So it's 0.047 as a decimal. So 0.047 to the 5th. Okay, so if I add those numbers together inside the parenthesis, we get 1.047 to the 5th. And then from here, I can just enter it into my calculator. Again, I do this part first. Do 1.047 to the 5th first. Then I do times 10,000. And you get about 12,581.53. Make sure that you are checking your work on a calculator to make sure you are getting that answer. Because if you're not, you're entering something into your calculator wrong. Okay, so my final answer is Sally would have about, again, I rounded, $12,581.53. And that's it, right? So exponential growth is just using that same equation over and over and over again. And then the good news is that for exponential decay, right here on the right, and if this says growth, cross it out and write decay, okay? So for exponential decay, it's the exact same equation. The only difference is now I'm subtracting 1, or I'm doing 1 minus the rate instead of 1 plus the rate. Okay, so A here is still my initial amount, so that has not changed at all. R is now my decay rate, right, instead of growth rate, but it still has to be a decimal. And then T is still time. So nothing has really changed here. So let's look at example 1. Oh, sorry, example 4. The exponential function below models the value of Melissa's car, where x represents the number of years since she purchased the car. Okay, so what does the 28,000 represent in the text of the problem? Well, that's my initial amount, so that must be how much she paid for it, right? The cost of the car when she bought it. So that's how much she paid for the car. And you don't have to write it in those words. You can write that's how much she paid for the car or whatever, okay? Then here, what is the rate of decay? Okay, so instead of, so here, the base of my exponent is 0.86. And instead of that equaling 1 plus r, now equals to 1 minus r. Okay, so I'm going to solve this. I minus 1, I get negative 0.14 equals negative r. So I get that r is equal to 0.14. Right, when I just divide by negatives. So as a percent, excuse me. I wrote the 4 before I wrote anything else. Okay, so 0.14. If I move it to the right 2 units, because it's always 2, I'm going to get 14%. So the rate of decay is 14%. So the value of her car is decreasing by 14% every year. It's a lot. Okay, let's look at another one. Example 5. A student population in a local high school is 1375 and is decreasing. That's interesting. That doesn't happen very often. It's decreasing by 2% each year. What will the student population be after 7 years? So let's write the equation. F of x is equal to my initial amount, which is 1375. Then I have 1 minus 2% as a decimal. Move it over twice is 0.02. So 0.02. And I want to know what it's going to be after 7 years. So this gets me 1375. Now, if I have $1 and I minus 2 pennies, I'm left with 98 cents. A very common thing is that people think that if the decay is, or if the problem is decreasing in value, that all they have to do is put in a negative 0.02. That is not how it works. It's always 1 minus the decay rate. Okay? Make sure you try this in your calculator to see what you get. But remember that we're talking about people, whole items, so we can never have a decimal, and you always round down. How many whole people are there? So I can say that the population will be about, not exact, but about 1,194 students. Right, so this is how we can use data that we're given in the real world, right, to help model situations and help predict what's going to happen. Okay, last one here. Example 6. An endangered species only has 400 animals left in the wild. If the species is decreasing by 6.5% each year, How many animals are left after 4 years? So let's write the equation. I'm starting with 400 animals, and then I'm decreasing 6.5%. Move it over twice, and I get 0.065. So 1 minus 0.065, and I want to know after 4 years. So I have 400. 1 minus 0.065 is 0.935 to the fourth. Remember, again, you should not have a negative here. So I get, and again, we're talking about animals, whole objects that cannot have fractions. And so what we always have to round down. So we're left with about 306 in 4 years. So word problem, so we have to answer in a sentence. There will be about 306 animals left. And that's it. So it's really just the same process over and over and over and over again. You just have to know what numbers to plug into, right? We're also going to talk about today about half-life. And then we'll be done. So let's jump back over to our notebook, or turn the page in our notebook or whatever. Clear this. And we're going to talk about half-life. Half-life is a term that's used a lot in a lot of different sciences, especially like, in figuring out how old artifacts are that are found or things like that, or how old, when they find like dinosaur bones, they can figure out how old the dinosaur bones are. It's actually really cool. So the definition of half-life. So the half-life of something is how long it takes. So what's the time, how long it takes for the initial amount to decrease by half, right? So if I start with 400 animals, like in that last problem, how long will it take until there's only 200 animals left? And however many years in that example, however many years that is the half-life. Okay, so how it's normally written is f of x is equal to a times 1/2, because I want to decrease by 1/2, to the t over h. A is still your initial amount. Okay, 1/2 is there because I want to decrease by 1/2. H is your half-life. That is the time, right? How long it takes to decrease by half, where t is the time. And so I'll show you how this works. So make sure you have this equation written down, because we're going to reference it here. We have 2 examples to do. Okay, so our first example, radium-223 has a half-life. Oops, I didn't write half. Has a half-life of 12 days. That means every 12 days, the amount of radium-223 that you have decreases by half. Okay? So the question is, if today, comma, you have 100 grams of this isotope. Ooh, we're using science words. How much would you have after 36 days? Okay, so I'm told that it cuts in half every 12 days. I start with 100 grams. I want to know how many I have after 36 days. So f of x is equal to, my initial amount is 100. I have that 1/2. My time is 36 days, and my half-life is 12 days. These have to be the same unit. If one is days and one is years, it doesn't work. They have to be the same unit. So just make sure that you're paying attention, okay? So because they're both days, we're fine. So this gets me 100 times 1/2 to the third. And if you enter this into your calculator, right, you will have about 12.5 grams left. So 1/2 to the third is 1/8, and then 100 times 1/8 is about 12.5. Okay, let's do another example of this, and then we'll be done. All right, so here we have, you start with 275 grams of an isotope. So I don't know what the isotope is. It doesn't really matter. Okay, oops, that's not the end of the sentence. And this isotope doubles. So instead of cutting in half, it multiplies by 2. So this doubles every week. Okay, how much would you have after 21 days? Okay, so let's write in our equation. F of x equals my initial amount, 275. Now, I am not cutting it in half. I am doubling it. So it's going to be a 2 instead of a 1/2. Okay, and then how much would you have after 21 days? So my time is 21, and my double life is 1 week. But this is days, right? And then 1 week. That doesn't work. I can't have that. I can't have days and weeks. So I either need to change 21 to weeks, right? So 21 days equals 3 weeks. I could do that. Or I need to change 1 week to 7 days. And it doesn't matter which one you do. You'll get the same answer either way. But you can't have one be in days and one be in weeks. So I'm going to go ahead and change this to 21 days over 7 days. And 21 over 7 reduces, so I have 275 times 2 to the third. 2 to the third is 8. 275 is about 2,200. So you will have about 2,200 grams. So just make sure that we're paying attention to our units, right? Are they both in days? Are they both in weeks? Are they both in hours? Whatever it is. Just make sure that we're paying attention to that. Okay, we do have some practice on this today. But that is it for the notes. If you have any questions along the way, make sure you reach out, and we'll see you later.